Okay, I hope I'm audible to all students who are attending this lecture of Mathematical Methods for Economics, Part 2. Okay, we intend to start with a new topic within the MME-2 course. This is functions of several variables. Formally, this is chapter 15 of the book I prefer to follow for my MME-2 course, which is Sater and Hammond. The fourth edition of this book. Okay, so if all students can recall that in my MME-1 course, we had done functions in one variable. So if all of you can recall, we had y as a function of x. We used to find the domain of the function, the range of the function. We used to work out the inverse function. We had talked about one function and onto functions. All this was covered in my Mathematical Methods for Economics Part 1 course. Now, what is new in this particular course is now y is not going to be a function of only one variable, but it's going to be a function of many variables. If I directly link it to microeconomics, all of us know that quantity demanded is not only a function of own price. It also depends on price of substitutes and complements, income of the consumer, taste and preferences, and so on. So we can now write the introductory definition first. A function f of two variables, a function f of two variables x and y with the domain capital D is a rule that assigns a specified number f of xy to each point x comma y in the domain. Okay, so a function f of two variables x and y with domain capital D is a rule which will now assign a specified number f of xy to each point x comma y in the domain. If I show this to you using a diagram, remember we used to draw diagrams like this in the MME-1 course. This is my domain. This is my codomain. And all of you can recall all the elements in the codomain which have a pre-image in the domain are called the range. So now students, now how will our domain look like? Our domain is going to be now like this: x0, y0. It's going to be an ordered pair: x1, y1, x2, y2, x3, y3, and so on. And now my function is f. So x0, y0 will be mapped to f of x0, y0. x1, y1 will be mapped onto f of x1, y1. x2, y2 will be mapped onto f of x2, y2. x3, y3 will be mapped onto f of x3, y3, and so on. So now my domain is going to consist of an ordered pair. Or if I speak in more technical terms, my domain will now consist of vectors in 2 dimensions. All of you have studied with me the concept of vectors in the MME-1 course. x0, y0 itself is a vector in 2 dimensions. x1, y1 is a vector in 2 dimensions, and so on. So now my function is mapping the vector in 2 dimensions to a real number. F of x0, y0 is a real number. it can be a real number. F of x1, y1 can also be a real number, and so on. Okay, so now if you all can recall in the MME-1 course, when we had, I can spot the difference for all of you. In the MME-1 course, we just had y as a function of x. So our diagram was like this. Domain, codomain, we just had x0, x1, x2, x3, and so on. And then we had the function f of x0, f of x1, f of x2, f of x3, and so on. This is what we had done in the MME-1 course. Our domain was the set of values taken by x. Our codomain consisted of all the images formed by the domain in the codomain, which we used to call as the range. Now you can see the difference. This was what we had done in the MME-1 course. This is now a part of MME-2 course. So now my domain consists of vectors in 2D, 2 dimension. Okay, so hoping all students have understood this definition and the pictorial representation and have no doubts. Okay, so now we can do a very simple practice question which makes it more easy to understand. So consider the function f defined by f of xy equals 2 times x plus x square y cube. Suppose this is the function given to us. You can see the function consists of two variables x and y. The question asks you find f of 1 0, f of 0 1, f of minus 2 3, and f of a plus 1 comma b. It's a question which I have taken up from the book Sitsater and Hammer. So quickly, if we solve it, we are given the function f of x. How will I find out f of 1 comma 0? Put x as 1 and y as 0. Gives me 2. F of 0 comma 1 will be put x as 0 and y as 1. You get 0. F of minus 2 comma 3, likewise put x as minus 2 and put y as 3. This is minus 4 plus 4 into 27, which is 108. It comes out as 104. And if I ask you what is f of a plus 1 comma b, put x as a plus 1 and put y as b. So it's going to be 2a plus 2 plus a square plus 1 plus 2a times b cube. You can simply open up the brackets. Okay. So this was a very simple question. Objective was to just tell you that if we are given the function f of xy, how can we find the images formed by 1 0 0 1 minus 2 3 and a plus 1 comma. Okay, so now we can generalize it and we can write it like this. So I can write the generalization so a function f of n variables a function f of n variables which are x1, x2, dot xn with the domain capital D is a rule that assigns a specified number f of x1, x2, dot xn to each n vector x1, dot xn in the domain. So this is not new. This is just a generalization to the nth dimension now. It's like saying that now I have a function. Okay. Now I have a function which is mapping the nth dimension vector to its image f of x1, x2, xn. This is my domain and this is my codomain. Again, we will keep on having different values. You can think of it as x10, x20, xn0. Similarly, this is going to be x10, x20, xn0. These are going to be one set of values. I can draw another set of values x1, x2, dot xn with superscript 1 will be mapped onto. It will be mapped onto f of x1, x2, dot xn with superscript 1 and so on. So now my domain consists of a vector in the rth in the nth dimension, and you can see the image will be nothing but a real number f of x10, x20, xn0 and so on. These are all real numbers in the codomain. So the generalization, I hope every student has understood this. We can write some examples of functions. So if you look at the examples, so how will I write a linear function? So a linear function in n variables would be f of x1, x2, dot xn, which is going to be a1 x1 plus a2 x2 plus an xn plus the constant b. Okay, where a1, a2, an and b are constants. Now all students can recall in the MME-1 course when y was just a function of x. How did the linear function look like? Ax plus b. This used to be the linear function y equal to ax plus b when we had y only as a function of x. But now when we have a function based on n such variables, this is how I can now write my linear function. This is how my linear function is now going to look like. Another example I can take with all students. Remember the Cobb-Douglas function which we had done? So another example would be x1, f of x1, x2, xn. I can write a x1 to the power a1, x2 to the power a2, multiplied continuously till n, xn to the power an, where capital A, small a1, small a2, dot small an are constants, and capital A, which captures the technology basically, is greater than 0. If you all can recall, we had done the basic Cobb-Douglas production function. So basically, output y is a function of capital and labor. We can apply this to microeconomics. Output is a function of capital and labor, which I can write like this: a k to the power alpha, l to the power beta. This is in microeconomics, this is called a standard Cobb-Douglas production function, where Y denotes the output produced, K stands for capital, L denotes labor. So this is the Cobb-Douglas production function when we only have two inputs, capital and labor. But suppose I have n inputs. My Cobb-Douglas production function generally would look like this. Okay, so hoping that students have understood this and have no doubts. And similarly, the third example, which would be as follows. Now in statistics also, we can find this example in statistics also. In statistics, okay, if we have n observations, then all of us know how do we calculate the arithmetic mean. Arithmetic mean is nothing but sum of all observations. So if these observations are x1 plus x2 plus dot 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 xn divided by n. This is how we calculate arithmetic mean, sum of all observations divided by total number of observations. How do we find geometric mean? Again, you have learned this in basic statistics in high school. Geometric mean. So arithmetic mean, I can write x a bar, which is nothing but x1 plus x2 plus xn divided by n. Geometric mean is nothing but the nth root of product of all these observations, which is nothing but xg bar. And in statistics, there is also something called as harmonic mean. Harmonic mean is defined as 1 upon n times 1 upon x1 plus 1 upon x2 plus dot 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 1 upon xn. This we denote as the harmonic mean. So clearly the reason for taking these examples is to make all students understand in which all areas can you apply the concept of functions of several variables. You can find them in microeconomics, macroeconomics, you can see them in statistics. Arithmetic mean, you can see it's a function of n variables. Geometric mean is the nth root of all the product of n observations. Harmonic mean is the reciprocal of the sum of the n observations, and so on. Okay, and clearly you can see out of arithmetic mean, geometric mean, and harmonic mean, only arithmetic mean is a linear function. It is a linear function of the xi's. x1 plus x2 plus dot 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 xn divided by n. Geometric mean and harmonic mean, both of them are non-linear functions of xi's. Okay, if you look at the arithmetic mean, only arithmetic mean is the linear function of xi's. Otherwise, geometric and harmonic mean, both of them are non-linear functions of xi's. So I hope all students have understood till here and have no doubts. Okay, moving forward now, let's look at how to find the domain. So the heading is how to find the domain of a function of two variables. So we in our lectures in the MME-2 course will be focusing mainly on two variables, x and y. So now all students can recall the rules of domain covered in my MME-1 course in the topic functions. In my MME-1 course, we had lectures on functions, and all of you can recall what were the rules. So if I have a function root A, so root A is defined if and only if A is greater than or equal to 0. Any term within the square root should be greater than or equal to 0 for the square root to be well defined. Similarly, the second rule, the reciprocal function 1 upon A is defined if and only if denominator is not equal to 0. Third rule which we had done was if I combine 1 and 2, 1 upon square root of A. Now this is defined if and only if A is greater than or equal to 0 and A is not equal to 0. Together I can say A is strictly greater than 0. If A is greater than or equal to 0 and at the same time A is not equal to 0, together they mean that A is strictly greater than 0. And the fourth, all of us know log of A. Ln of A is defined if and only if A is strictly positive. Because all of us know from the MME-1 course, ln 0 is minus infinity, where ln denotes natural logs. Ln 0 is equal to minus infinity. So ln function is well defined only if A is strictly positive. So all this was covered in the MME-1 course in my lectures on the topic functions. I am revising it again in this lecture so that we can solve questions now, but for functions based on two variables. So now let me do some practice questions which make more sense. Okay, so practice questions. Determine the domains. Determine the domain of the following functions and draw the sets in the xy plane. So they are as follows. First question, f of xy is square root of x minus 1 plus square root of y. So we need to find the domain of this function and we need to draw that set in which this function is well defined. So I can do one question for you so that you can understand it. You can clearly see that f of xy is the sum of these two terms. Now square root of x minus 1 is well defined if and only if x minus 1 is greater than or equal to 0, which implies x is greater than or equal to 1. Square root of y is well defined if and only if y is greater than or equal to 0. So what is the domain of this function? Set of all vectors x comma y belonging to the two-dimension space such that x is greater than or equal to 1 and y is greater than or equal to 0. This is now the domain of the function f. So if I plot the diagram, how will the diagram look like? So this is my x-axis, this is y-axis. X greater than or equal to 1, how will I plot it? X equal to 1 will be this line. And x greater than or equal to 1 means all shaded area to the right of 1. This is x greater than or equal to 1. Y greater than or equal to 0 means y greater than or equal to 0 means the positive y-axis. This is my y greater than equal to 0. So what is the intersection, guys? Where you have both the black and the red line. So my intersection is given by this area. That means I can say this is my region S over which the function f of xy is well defined. So I can call this as the set S. Set S is nothing but the set of pairs x comma y such that x is greater than equal to 1 and y is greater than equal to 0. And this is the region where the red and the black lines are intersecting each other, which I have shaded in blue color, and we have called it as the set S. So I can say, therefore, f of xy is well defined over the set S, where set S is nothing but the domain of the function. So hoping all students have understood this question and have no doubts. Okay, erasing this off, let's look at the second question. Now again, it's the same. Determine the domain of the following function and draw the set in the xy plane. So now we are given the function g of xy, which is 2 upon the square root of x square plus y square minus 4 plus the square root of 9 minus x square plus y square. Let's solve this question. So when is g of xy well defined? If I use the same rules, g of xy is well defined if and only if x square plus y square minus 4 is strictly greater than 0, because it is within the square root and in the denominator as well. And 9 minus x square plus y square is greater than or equal to 0. You can clearly see I have applied the rules of domain which we have learned in this lecture. Now this implies x square plus y square is greater than 4 and x square plus y square is less than equal to 9. So I can say, what is the domain of the function? Set of all x comma y belonging to the two-dimension space such that x square plus y square is strictly greater than 4 and less than equal to 9. Now guys, if I plot the diagram, do you observe something? Recall x square plus y square equal to 4 is the equation of the circle with center at 0, 0 and radius equal to 2. And x square plus y square equal to 9 is the equation of the circle with center at 0, 0 and radius equal to 3. Now we had learned this in my MME-1 course in our lectures on coordinate geometry. If you all can recall, we had done the concept of straight lines, circles, parabolas, hyperbolas. All this was covered in my MME-1 course. What was the general equation of a circle? X minus alpha square plus y minus beta square equal to r square. This was the general equation of a circle with center at alpha comma beta and radius equal to r. So for this particular question, if I plot the diagram for which I am erasing the initial part of the screen, how will the diagram look like? So erasing all this off, because we also have to draw the diagram as per the question. So we have the x and the y axis. And you can see, first of all, we are plotting x square plus y square equal to 4. It's going to be a small circle with the center at 0, 0. And the radius is 2. So this is 2, 0, 0, 2, minus 2, 0, and 0, minus 2. Okay. And then I have another circle, the bigger circle, with the radius 3. The center still remains the same, but now we have 3, 0, 0, 3, minus 3, 0, and 0, minus. Now let us do the shading. X square plus y square strictly greater than 4 would mean shading will be outside the smaller circle. X square plus y square greater than 4 means shading is outside the smaller circle. All the red shaded area you can see. This is the shaded area for x square plus y square strictly greater than 4. And x square plus y square less than equal to 9 means shading will be towards the origin. Now, how do I shade the area towards the origin? It's going to be like this. So from the bigger circle, we are shading the area towards the origin. So now, which is the portion which is overlapping? Look at that portion which consists of both red color and blue color. That is given by this region. So this particular purple region, which all of you can see on the screen, consists of red color also and blue color also, which is my required set S, over which the function g of xy is well defined. Okay, so the shading is something which you have learned in solving inequalities. X square plus y square greater than 4 will be the area outside the boundary of the smaller circle. X square plus y square less than equal to 9 will be the shading towards the origin from the bigger circle. The overlapping portion is nothing but the purple portion, which is my set S for this question. Okay, so this is where I intend to stop in this particular lecture. The purpose of this lecture was to introduce to all students the concept of functions in several variables, where we have primarily looked at how to find the domain of a function, particularly in two variables x and y. So we will continue with our lectures on functions in several variables, and in the next lecture we will actually talk about the concept of level curves, which is a very important concept we do in our lectures on functions in several variables. So I stop in this lecture. I hope all students have enjoyed this lecture. Any doubt, you can unmute your mic and ask, or call up or mail me your doubts at divineschooloфeconomics@gmail.com.